All right, I think we're ready to get started. Can everyone hear me okay? Glad to see we have a full house here. Welcome to the annual Beckman Brown Lecture on Interdisciplinary Science. I'm Steve Marin, the new director of the Beckman Institute. Well, I won't be official till the Board of Trustees meets Friday, I think. But I'm pleased to welcome everyone here today. The Beckman Brown Lecture on Interdisciplinary Science honors the late Arnold O. Beckman, the founder of the Institute, and Dr. Ted Brown, the Institute's founding director, who is with us today. The Arnold and Mabel Beckman Foundation endowed this lecture series to celebrate both Arnold and Ted. They also endowed a Beckman Brown Interdisciplinary Postdoctoral Fellowship to support trainees engaged in collaborative work at Beckman. And the 2024 Beckman Brown Postdoctoral Fellow is Si-Jun Chao, who's here today somewhere. I don't know if you want to raise your hand. He's way back there. Congratulations, Si-Jun. Today I have the distinct honor of welcoming Ted back to the Beckman Institute for the lecture today. Together, Ted, Arnold, and Mabel champion the idea of creating a physical space, the Beckman Institute, that transcends the traditional boundaries of academia. Because of their vision, we're all here crossing disciplines, breaking barriers, and making human health and well-being better. So before I introduce today's speaker, I'd like to ask Ted to say a few words. Ted?
Thank you. Thanks very much. Gosh, it's been a while since I've stood up here. I am so grateful to be here today. It's wonderful. It's just for me to be thankful. I never stand up here giving a talk without making the point of thanking the Arnold and Mabel Beckman. Those people have made all of this possible for us, and I can't thank them enough. And that includes also our gratitude for the postdoctoral fellowship and the lectureship. I'm not going to get in the way of any of the rest of the procedure. I just want to make sure that you understand how grateful I am. I mean, when I come in this place, it really makes me feel warm. It looks the same as always, except, of course, for the 20 or 30 yards of construction plywood that you saw coming in the door. But that's all in a good cause, believe me. We are going to open, they will open, a beautiful new cafe there by the end of the year or so. And I think we'll all be grateful for that when it happens. So let me get out of the way and introduce, well, I don't have to introduce you because you're already introduced. I'll give it back to our director.
Thank you, Ted. Thanks so much, Ted. And just a historical note, Ted was the director when I was an undergraduate student here, and Susan Martinez was a graduate student. So there's a lot of history here. Today we are honored to welcome Dr. Stephen Chu as our Beckman Brown lecturer. He is the William R. Keenan Jr. Professor of Physics, Molecular and Cellular Physiology, and Energy Science and Engineering at Stanford University. Dr. Chu received an AB degree in mathematics and a BS degree in physics from the University of Rochester and a PhD in physics from the University of California, Berkeley. Before taking his current faculty position at Stanford, he was a staff scientist at Bell Laboratories, where he also served as department head. Dr. Chu's scientific contributions are far-reaching and include developing the first optical tweezers to manipulate biomolecules, precision atom interferometry based on optical pulses of light, and single molecule FRET of biomolecules tethered to surfaces. In recognition of his work, he's received many awards and prizes, too numerous to list, but most notably was awarded the 1997 Nobel Prize in Physics for methods to cool and trap atoms with laser light. He's now developing and applying new methods in molecular biology and medical imaging. He's really changed fields, material science and batteries. In addition to his research appointments, Dr. Chu has served as the U.S. Secretary of Energy, where he began ARPA-E, the Energy Innovation Hubs, and was tasked by President Obama to help BP stop the Gulf oil spill. He has also served as director of the Lawrence Berkeley National Laboratory. At Stanford, he led efforts to develop BioX, an interdisciplinary biosciences research institute that linked the physical and biological sciences with engineering and medicine. Sounds kind of familiar. He is past president of the American Association for the Advancement of Science and a senior advisor to the directors of the NIH and NSA. Among his many accomplishments, Dr. Chu has 35 honorary degrees and is member of the U.S. National Academy of Sciences and 8 foreign academies. Please join me in welcoming Dr. Chu.
Before I begin, there are about 10 seats. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 seats, 16. Okay? So I will wait a minute. Actually, I could use 5 more minutes to prepare my talk, but never mind that. Okay, good. All right. 1, 2 more, 3 more, 4 more, 5, 6, 7, 8. Don't be bashful back there. Okay. All right. Anyway, it's a great pleasure to be here and to be talking at the Beckman Brown Lecture, to meet Professor Brown, who's amazing. Where'd he go? There he is. So without further ado, I'll just begin and talk a little bit about what's going on. Just to remind you, the temperature of the Earth is increasing. This is a record from 1850 to June of 2024, and you see that the temperature has increased, and in the last decade, it's seeming to pick up. In addition to that, if you look at the land only, by the way, this is the UN goal 1.5 degrees right here. So we are going past 1.5 degrees. We will almost certainly go past 2 degrees and probably 2.5. Another thing I should remind you of is that the land and sea temperature, that was the global average of land and sea. Sea is 70% of the surface area. Land temperature has gone up higher. It's above 2 degrees. And the message here is that the ocean warms up more slowly than the land. Think of the ocean average depth 2 to 3 kilometers as being like a set of ice cubes. You change the atmosphere of the Earth. If this energy coming in is the same, but energy going out is less, you have to warm something up. And the estimate is roughly 50 years to warm up the oceans to reach a new equilibrium temperature if we stopped emitting carbon dioxide today. So what we see today is not actually what we're going to see based on the damage already done. So that's a little bit scary, and this just describes what's happening. 90% of the energy since the greenhouse gases started to accumulate is actually gone into the oceans, not into the surface. What does it due to? Well, it's due to number of greenhouse gases. The most common greenhouse gases due to humans are carbon dioxide, methane, and N2O. And so this is a record from year 1 AD to the present time. And you see that it's only in this last little period that you've seen sharp increases. Where are we heading? Well, it depends on what we do. But this is a graph of, now this graph includes climate predictions, and I just should say at the outset there are large uncertainties in the climate predictions, but it also includes scenarios of what climate policies there will be. And so with no climate policies, you see the big uncertainty is where we'll end up. This is 1990 to the year 2100. These are current policies, and then pledges and targets. So this is 1.5 and 2 degrees. I want you to pay particular attention to the y-axis. This is the number of billions of tons. This is 50 billion, 50 gigatons of carbon dioxide equivalent emitted every year. And in order to get to 2 degrees, you have to go to 0 emissions in everything by 2100. That means everything. not just electrical stuff. So where are we now? We're here. We're a little bit above current policies. And so the trajectory of where we end up will, of course, depend on what happens in the future. The World Bank has estimated that there may be 200 million climate refugees by 2050. Already there have been 10, maybe 15 million climate refugees that have gone to Europe and other places. And that has actually changed the politics of the world. The number of displaced people due to refugees, most of the refugees are refugees from economies that collapsed, from gangsters that have taken over countries in Central America, from the war in Ukraine, other things like that. But the climate refugees are beginning and are expected to increase. So that's another thing we have to be concerned about. And then finally, you can ask, okay, if greenhouse gas emissions have to be decreased, where are they coming from? And this is one thing that I got from the IPCC, which is estimating what's happening. And if you look at this graph, you have to see that food, agriculture, land use, roughly in round terms is 1/4 of all greenhouse gas emissions from agriculture, from fertilizer production, fertilizer use, and from N2O emissions, and the rest of it is over here. So the elimination of greenhouse gases means not just decarbonizing the electrical sector or personal transportation, for example, going to EVs or going to wind and solar and other things like that. It really means the elimination of all sources of carbon, including that made in steelmaking, concrete, plastics, chemicals, textiles, and all forms of transportation. And as I said before, conservatively, people say food production, 25% of all greenhouse gas emissions. Okay, so I'm going to talk a little bit and put it into historical context, and I think the study of history is very important. And let me emphasize that by showing you this cartoon. Those who don't study history are doomed to repeat it, yet those who do study history are doomed to stand by helplessly while everyone else repeats it. So I feel like one of these people. And so what about this? Well, historically, about the dawn of the Industrial Revolution. There were actually several industrial revolutions. Here we see this beautiful picture of the iron horse, the steam locomotive, replacing horse-drawn power, and you transition from animal and human power to horsepower. Another bit of historical context was in Henry Bessemer invented a way to produce steel economically at scale. Steel was discovered millennia ago, but it was Henry Bessemer. And what did he do? Well, it was during the Crimean War that England needed stronger material to replace the cast iron cannons because the explosives, the chemicals were better, and the cannons would fly apart. Let me remind you what the Crimean War was. It was when Russia invaded Crimea and England and France decided to fight back. Sound familiar? So anyway, let me continue with some of the other industrial revolutions. You've all heard of the invention of the transistor at Bell Labs. John Bartine, Walter Brattain made the first point contact resistor and got the original Bell Labs patent in 1948. Their department head was William Shockley, Bill Shockley, who was incensed that his name was not on the paper, that he didn't have anything to do with it. But he was a genius and a department head. And so he holed himself up in a conference room. He was supposed to tell about what the quantum mechanics was to tell us about condensed matter solid-state physics. And so in a few days, he developed in his hotel room the semiconductor theory of the p-n junction and transistors. So he deservedly got his Nobel Prize because he did a lot of the groundwork theoretical stuff that laid the basis for the next 20 or 30 years. But the transistor would not have happened if it had not been for something else. And this was the ability to purify first germanium, then silicon. This is Bill Fan, zone refining, where you have a slug of germanium, you have a heater, you melt the germanium, you let it solidify, and this heater goes up and down the tube. And in the interface between solid and liquid, it chases the impurities down the tube. And in so doing, he could get germanium really, really pure so that you can actually dope it to what you wanted. And it was that invention that allowed mass production of transistors. I was a young scientist at Bell Labs. In 1978, there's this old guy who, office next to me, he would totter and he'd come in, he'd kind of do something, he'd close the door, some people would go, say hello. After a couple hours, he would leave. I finally asked my department, who's this guy? And he said, you don't know, that's Bill Fan. And I said, who's Bill Fan? He said, he made the transistor possible. And he says, you remind me of these two cavemen. You know, they're young cavemen. They're watching this old guy go by. Who's this guy? And the other guy says, you don't know who it is? No, what did he do? He invented the wheel. And the other guy says, what did you do lately? Anyway, there was also Thielsen Sparks invented another way to purify germanium and then silicon. So it was the ability to make high quality materials that allowed this invention to be commercialized. You get a Nobel Prize for optical fiber communication, but it was Corning and then Bell Labs that actually made super pure optical fibers that allowed you to transmit over long distances with low loss. And similarly, this may sound like an advertisement for Bell Labs. It is. The silicon photovoltaic cell was invented accidentally at Bell Laboratories. And it was 20 years of continuous improvement that allowed this to happen. So it was actually material science production development methods. Okay. Now, where are we going? Since then, in silicon photocells, there's a new kid on the block. The verdict's not in as to whether this is going to replace silicon, but many people are very excited. They're called perovskite materials. They're very complicated materials. So in this section over here, you see kind of a structure of what this looks like, and then it's being deposited on thin films. Over on the right-hand side, in terms of time, you see perovskite plus silicon perovskite in multiple layers and other perovskites, and you see that if you look at the photovoltaic development, they are beginning to plateau, but all of a sudden the new kid on the block is surging ahead. There is great hope that this material will be long-lasting. 2 years ago, it would last several months. Now, accelerated live testing says it's at least 15 years, and the prospect of getting to 20, 25, 30 years looks very good. And so it's very inexpensive material. You can put it, you only need 0.3 of a micron of coating rather than 150 microns in silicon. And it's a very low temperature deposition, so the amount of energy used to make these things is very low. So, and the materials are inexpensive. So there is intense excitement that perhaps you can get 30% or higher, 35% photovoltaic cells in dual layer perovskite cells. So it's all very good. I should also say that there's been great advances not only in silicon, but also in wind, and these great advances are wonderful. People say that wind and solar, the levelized cost of electricity is now that below of natural gas, which is one of the, in the United States, is some of the cheapest in the world, and so the show's over. And the real answer is no, not quite. They actually have to be twice as inexpensive as natural gas. The reason is, as you go to more and more wind and solar and other renewables, you need enhanced transmission and distribution systems, you need backup power of some kind, and you need energy storage. And so that's the real costs of all the things. If you're 10 or 20 or 30%, wind and solar, it doesn't matter. California is now 70% carbon-free electricity. And we see some of the issues that are emerging as we go from 70%, of which 10% is nuclear, to 80 and 90%. Much more energy storage is needed. And energy storage is expensive, transmission lines, also needed, also very expensive. It's possible to construct very efficient, high-energy, high-voltage transmission lines. China, this is a picture of a 1.1 million volt DC line. DC is good because even at 50 or 60 cycles, there is a little bit of radiation loss. So there's only resistive loss. There's no coupling of the alternating fields into the ground, which also lead to loss. But these are very big. These are the high voltage standoffs of this voltage, and those things over here are people. So it's big. It's expensive, but these transmission lines carry 6 billion watts of power. And so that this economy of scale allows them to do this. You can send a transmission line to 3,500 kilometers, lose 5% of the power. Okay, so you don't actually need superconducting. Europe is beginning to link itself together with high voltage DC lines. Iceland is very rich in renewable, mostly hydropower and a little geothermal, also Norway. And so they're beginning to make plans for all of these things, linking it together. The United States is a little bit behind because we have many, many utility scales systems, and people in areas where there's cheap electricity don't want the electricity to go away from them, let's say the state of Washington and Oregon, where there's a lot of hydropower, to places like California, because their prices may increase. The overall prices will go way down, but they want to keep cheap electricity there. New England wants to keep the utility energy providers of New England don't want cheap hydropower from Canada because the capital investments they made in gas plants, for example, become stranded. And so there is politics in this because there's money involved in this. And if there's anything I want to convince you of, energy is really about money. And it actually does make the world go round. So, okay, so let's talk about other materials and resources that we need. And in order to do that, I want to step back and take a broad view of what do we take out of the earth and use. So in this graph, on the y-axis is the annual world production in tons, metric tons of stuff. And over here in this red box, you see 2 types of things we use. One is oil, coal, natural gas, steel. The other is concrete, asphalt, cement, and non-fuel woods. So it's either construction material or it's energy. Down here, each tick mark is an order of magnitude. Down here, you begin to get aluminum, copper, zinc. These blue things over here are chemicals. They're polymers, plastics. And the feedstock of plastics are fossil fuel. So most of what we use is either energy-related, fossil fuels and steel, or building-related. And so that's one of the things you should be aware of. Another thing is what's happening with this demand. People are talking about shortages of cobalt and nickel for the batteries used in today's electric vehicles. That has already begun to shift people to produce cars using iron phosphate instead of manganese, nickel, cobalt, NMC batteries, because it's become too expensive. But one of the things that is looming, we don't know when it'll occur, whether it's 50 years from today, 40 years, 80 years, somewhere around that time scale, we're going to begin to run out of copper. And that's a problem. And so the question is, what do we do when we begin to run out of copper, especially with increased electrification, which is in everybody's plans? What do we do with the copper? And to the young people in this audience, I dangle in front of you something, and that is there are forms of carbon, like carbon nanotubes, graphene, on a per weight basis are comparable or better than copper. And guess what? We have tons of carbon. In fact, we have so much carbon that even though the demand for petroleum and natural gas have been increasing year after year after year for many, many decades, The reserves are also increasing relative to the demand. And they don't actually are seriously looking for natural gas quite yet, because it's a byproduct. And so there's a ton of natural gas in the ground, but it's a bad greenhouse gas. But if we can turn natural gas into a conductor or into a structural material, it's a whole different ballgame, because that doesn't find its way into the atmosphere. Okay, speaking of copper and electrification and everything, there's energy being used in many things, and here's an energy forecast in a paper written, I think, in 2015, of the energy demand in computation and communications. And the blue is wireless and wired communications. This is the energy used in production of ICT is internet communication, these things. These are consumer devices, television, computers, mobile phones. This fraction is going down as they get a little bit better. A widescreen LED TV is like 300 watts. So it's not inconsiderable. These big ones that you have in lecture rooms, those are a couple of kilowatts. A toaster, I've got one in a lecture room just outside my office, and everybody leaves it on. So every time I go in there, I turn it off. There's a sign that says, please don't leave this on, but it's always left on. Imagine a toaster left on 24/7. It's kind of gross because, the building's air conditioned as well, so you're paying twice for it. But anyway, this green thing is of concern. That's data centers. But this article was written before machine learning and artificial intelligence have gone in full swing. It was written before blockchain technology is really taken off. About half the energy of data centers is used for mining Bitcoins and stuff like that, of which most of the application of Bitcoin is in money laundering. So I'm not a fan of Bitcoin. Sorry. I forgot this is a recent slide, but let me just say that the machine learning and artificial intelligence is a very big deal, and what it shows on a log scale is an inflection point where these large machines that give us AI like ChatGPT are really changing our lives. They're incredible. AlphaFold is an incredible program that's changed structural biology immensely. All good stuff, but they're using more compute power. How much compute power they're using? These data centers are in the hundreds of megawatts, 24/7. A single data center, but Google and AWS, Microsoft will have a bunch of these data centers churning out this stuff. And the question is, how smart are they? And you have to compare it to different architecture. For example, I had asked ChatGPT a year ago, who was the first elephant to swim the English Channel? And without blinking an eye, with great authority, they said, the first elephant was Jumbo. It swam from Dover to Calais in 1954. It was a heroic event. There was much joy and celebration everywhere. Okay? Really. Someone else did a thing. They put in a seven-sided object and said, what is this? And it came back, that's an octagon. Okay, ChatGPT does not know how to do arithmetic yet. They're working on it. So before you say it's an octagon, you have to understand octagon means 8 sides, and you have to be able to count. And some of the headlines in the recent month are said that they're trying to teach ChatGPT and other AI to count. So it doesn't come up with this stuff. Now, if you ask ChatGPT who Jumbo, they've modified the answer because I've talked about it twice. Other people have mentioned this. And so now they say it's Jumbo, but it was really a stunt. He didn't really swim the English Channel. He was ferried across in 1954 on a boat. All made up, but with great authority. Anyway, now compare this architecture, which is stunning, to something else. Other kind of compute power, like these things. This is a kid playing with his food, playing with gravity. You know, when a kid goes like this and throws his food like that, he says, ah. In the meantime, if those of you know, if you are parents and let's say you speak a certain language, your spouse speaks another language, and the graduate students aren't rich enough, but if they are rich enough to have a nanny, the nanny might speak a third language. By 4 years old, the child knows all languages perfectly, no accent, easily can go from one language to another depending on who they're talking to, mother, father, or nanny. Okay? And by the way, they can, one of the big events in machine learning was how did you tell the difference between cats and dogs? And kids can figure this out too. How much power they use? About 20 watts. Okay? And much less data. Much less data. And so ChatGPT has mined 99.9% of all the data. And so this is a real problem. Because then they mine the data in their queries, and the query answers to the queries become data, and now they're mining themselves. And so there's a little positive feedback. By positive feedback, I mean in electrical engineering sense, that's not all that positive. But okay, so yes, here's a childless cat lady. Sorry. So anyway, now, there's a slightly different architecture. We know some of the elements. It's a deeply connected nonlinear neural net. Hopfield talked about this in the 1970s, but we're not close to getting anything close to this performance. So if there's a goal we want to do, the brain is pretty smart, very low power, and could learn much faster. Why is that? Now, part of it is because they're interacting with the world. So there will be a new inflection point in machine learning and artificial intelligence, and that is when you get robots to interact with people and can actually talk to people and see the world instead of scarfing up things from the internet. You're in a totally different plane. And so this will happen sooner or later, probably in 10 or 15 years. You can start this, how many people talk to Siri or equivalent of Siri? Half the young people raise their hand, the other half probably do. Anyway, but they talk to something, or they certainly, anyway, so these are some of the issues. Now, the electronics thing, there are issues. There could be new revolution in semiconductors, may or may not. You never can underestimate silicon. It's been really interesting. CMOS technology is wonderful, but there's a new material called ferroelectrics. It's actually perovskites. The object is you use an electric field to align electron spins. Once the electron spins are aligned, you don't need any more power. And that's important because high-speed memory depends on charge on a capacitor, but the capacitor leaks. So you're actually using a lot of energy. And the high-speed memory in these high-performance computers use a lot of energy. And so if you can get ferroelectrics to flip on and off with much less power, operating at 150 millivolts instead of a half a volt to 1 volt, which is today's electronics, you're now looking at order of magnitude less power. There's architectures also. There's a 4.0 mini that's limiting the query that saves more energy. There's lots of stuff, but one of the people we recruited to join DOE, and he was head of the Sunshot program at the Department of Energy while I was there. Ramesh was a professor at Berkeley. He's now a vice provost for research at Rice, and he founded Kepler Compute, which is a company based using ferroelectrics to see if you can make both first high-speed memory and then logic. Whether it happens or not, we don't know. But these are some of the things. Okay, low-cost energy storage is absolutely crucial. This is a plot of how much energy you can store and how many days it's worth. And over here, PHS is pumped hydroelectric storage. That's lifting water up a hill and letting it come back down. 95% of all electrical energy stored today in the world is through pumping water up a dam and letting it come back down. Sounds pretty inefficient, but if you've got 100 feet or more, it could be 75% to 80% efficient round trip, excluding evaporation losses, because when you pump it up, some of it evaporates. But that's a big deal. If there is an existing dam, putting in pump storage is the cheapest form of energy storage by far. If you have to build a hydroelectric dam, that's another story, because there's a lot of resistance. A lot of people don't like to build hydroelectric dams. They want to, when I was Secretary of Energy, they wanted me to take down all the hydroelectric dams in the Columbia River because they said the dams are killing salmon. I said, no, we know that, but we're fixing it and are showing the salmon population coming back because we would have fish jump runs that bypass the turbines, and you have more fish-friendly turbines. And so it was coming back, and they said, and I said, besides, if there's climate change and the water's above 70 degrees, the salmon won't be in the Columbia River anymore. And they said, in all earnestness, they said, well, that's 100 years from today, or that's 2100, I said, so it was whatever, 80 years. And it said, we care about now, not tomorrow. Okay, so anyway, I said I'm not going to breach the dams. And I'm trying to convince the governor of California not to breach the dams because he is under similar pressure. Anyway, so pump storage, let me describe how it works. When the wind blows, the sun shines, you do the energy intensive thing, which is, for example, to pump water from a well. And then when you need the water, you open up the valve. And as I said, it's 95% of all storage. But we need other things because not everybody has hydroelectric dams, or there has to be transmission issues if you transport over long distances. So one of the possible ways of capturing chemical storage, but not in a conventional chemical battery, was just to store the molecule, for example, hydrogen. And it comes in many colors, more than I've shown here, but the gray hydrogen is you take methane out of the ground, you burn it, or you turn it, gray hydrogen is you turn it into hydrogen, and in this process of turning methane into hydrogen, you turn it, the byproduct to CO2, and you vent to CO2. This is the price, approximate price in the United States, $1.50 a kilogram. Blue hydrogen is you take the methane, you turn it into hydrogen, you capture the CO2, and you sequester it. Green hydrogen is you use renewable energy, carbon-free energy, or nuclear power, and these are the prices. But until you get carbon-free hydrogen down to striking distance of gray hydrogen, there's a great incentive to keep on using gray or possibly blue hydrogen. Blue hydrogen could be a transition. I don't see, it's not terrible, but in the long run, when you poke holes in the ground, we already know 2 to 6% of the methane comes out of the ground, it's not captured. And then when you capture it and sequester it, there are other issues. So in the end, you do want green hydrogen. Despite its flaws, green hydrogen can be used. It can replace coal in the reduction process of taking iron ore and turning it to steel, and it could be the industrial heat source, similarly with plastics, chemicals, fertilizer, aviation fuel. So these are all processes not associated with electricity generation, which emit a lot of carbon, and hydrogen can play a very important role in all of these. There's a problem. Hydrogen is leaky. It's a symmetric molecule, and there's no spectroscopic signature of hydrogen. It was only with remote detection of methane that we discovered that the gas fields were leaking a lot, and the pipelines were leaking a lot. In fact, when I was Secretary of Energy, the pipelines were leaking 1 to 2% of the natural gas in commercial pipelines that are feeding industry and homes. And, well, that's kind of crazy, 1 or 2%. And so then I discovered why. It's because the utility companies could charge for the leakage to their customers. And so I set about doing the only important thing, get the utility companies not to be able to charge what they leak. And suddenly they started plugging up leaks. I don't know why. because before that, they only wanted to plug up lease if there's a chance of an explosion. Okay, so money talks. Anyway, we need the way of detecting hydrogen. Is it possible? No spectroscopic signature? The answer is yes. You can make a miniature mass spectrometer that's this big. And you can make a chemical thing that's very sensitive to hydrogen that's also this big. If you can put it on a drone, and drones are getting better and better all the time, the drone can go up and down pipelines and detect the leak. So, but before you have that, there can't be any pipes, which means you have to move it through compressed air, which is very, very expensive. Compressed hydrogen, 10,000 PSI steel tanks. Okay, now there's a new kid on the block, and that is another friend of mine who I recruited to join me at the Department of Energy. Ravi Prasher is now the chief technology officer of a solid-state fuel company, and he wrote me an email 4 months ago and said, we just got a big breakthrough. Solid-state fuel electrolyzer is now at 88% efficiency. That means hydrogen to electricity, 88%. It also means electricity to hydrogen, 88%. This is good, because that means you can send electricity to where you need it, at the steel plant, at the refinery, at wherever you need it, or you can use it for industrial heat, but you use it on site so you don't have to truck it around. And so this is a very big deal. The downside of solid-state electrolyzers, fuel cells before were two things. They didn't last long, and they worked at high temperature. Now they last long. The temperature doesn't matter, because this is ground source. It's not on a truck or a car. And so we know from very many things, Haber-Bosch process, that high temperature chemistry works. Okay, let's go to conventional batteries. Again, where are we now? This is a plot on the x-axis is weight, how much energy, watt hours per unit weight, and how much energy per volume. For cell phones, it's only about energy per unit volume, because you want to pack more stuff into the cell phone. For cars, it's both. It's energy per weight and energy volume. This is where the batteries are going for EVs. That green circle is the current Tesla battery. Going to here, that's my projection, and it's based on the fact that I'm on the board of a battery company, and we're shipping samples at that density. So that means cars may follow within 5 or 8 years. Why so long? Because of the safety issues and it takes at least 4 or 5 years when you have a super tested battery to find its way into a car. The other good news about batteries is the cost. So this is on the y-axis, this is the amount of batteries being put into use, shipped out, used. And every tick mark is an order of magnitude of stuff made. And over on the y-axis is the cost, and that cost is also on a logarithmic axis. So when you see a straight line going down, you see that, and this is called a learning curve. For some reason, it applies to virtually every technology that we've ever known about. The more you produce, the better you get at making it work cheaper and faster. And so at the very beginning, batteries were just used for phones and computers and things. But as EVs took off around 2000 and beyond, you take a very, very steep learning curve. It's good news. By 2020, the prices had dropped to $100 per kilowatt hour. 20 years ago, it was $2,000. By 2030, I think $50 per kilowatt hour is likely, because the OEMs, the car manufacturers of the world, don't want to pay. $100 is their limit right now. And they're now asking, in a couple of years, I want $90, and in a couple more years, I want $80. And so that's great. I already talked about the nickel and cobalt. We've shifted to iron phosphate. But what about lithium? It too is important. And it turns out that it's possible to get lithium. There are lots of sources of lithium. Most of the lithium sources are very polluting. About 80% of the lithium is you take salt water out of the ground, you pump it up, you put it, make a big lake, and you let the salty water evaporate, and you've got 1 lithium atom per 1,000 sodium atoms. But then you refine using chemical process to get out the lithium. But in the act of doing that, you've pumped underground water up to the surface, which is extremely polluting. It's got all sorts of junk in it, heavy metals, slight radioactivity, all sorts of stuff. Furthermore, you've taken such much water out of the saline aquifer that the fresh water, which is always on top, sinks down. And so you're actually depleting your freshwater supplies as well. So it's doubly polluting. Now, the prospect of being able to take salty water, just take out the lithium and dump the rest back, is becoming a very real possibility. This is Chung Lu, who's now a assistant professor at the University of Chicago. She did her postdoc with me. She was a graduate student with Eastway. And we published a way of running a half a battery using iron phosphate. And you have lots of salty water, and lithium goes in more likely than sodium. And after a single pass, you can go from 1,001 sodium to lithium to 95% lithium. Since then, she continued to work at the University of Chicago. She now finds that you can take seawater at 20,000 to 1, and in a single pass, you can get 8 to 1 lithium to sodium. So now, if there's lots of, I don't want to go back. I don't have to go back. I can go forward. Where's the lithium? Lithium's abundant. It's about as abundant as chlorine in the Earth's crust. It's just that it's a dilute, and so there's lots of lithium around. Anyway, let me continue. Let's go back to the fact that we do need, eventually battery storage. You use pump hydro where you can, chemical battery storage. Even right now, if you do a techno-economic analysis of battery storage in the United States, which has some of the best renewable energy in the world, and we have 4 time zones, which is also good, in different weather patterns. So if the wind is blowing in Texas, it may not be blowing in California. It's okay. Europe is kind of one weather zone, so it's very different. But you will need turn-on power, compact turn-on power, until batteries become really cheap. How cheap is really cheap? Right now, they're $100 to $200 a kilowatt hour, and they need to be 10 or 20. And so that will require a bit of a breakthrough. So we don't have utility scale batteries at $10 or $20. $50 kilowatt hour for cars, they become comparable to internal combustion engine cars. The batteries in cars are a lot less expensive than utility scale batteries, because when a utility scale battery breaks down, you have a blackout. And occasionally a battery might break down, but that's okay. You're a single stranded car. So there are much more demands. So the choices are coal, natural gas, or nuclear fission. I should say, you can basically, what about fusion? And let me just say that there's been a lot of excitement because Livermore has shown that you can have a laser to induce fusion for the first time, more energy in the X-rays imploding the deuterium-tritium pellet than energy coming out. That's great. But they've had 3 or 4 shots. I'm collaborating on another project with the person who's designing the targets for this fusion project, and I'm good friends with Omar Hurricane, who's the scientist who made the thing happen. He was parachuted in because it wasn't working 11 years ago. The fusion project is supported by the Department of Defense, by the way, not by Energy, because they want mini H-bombs for other reasons. Anyway, that's a different story. But their target is, they got a couple of megajoules out, but it took days to prepare a single target, and the highest rep rate they can get is like 1 or 2 a month, and they got 3 or 4 successful shots. You would like it that it's commercial fusion would require 10 or 20 per second. And you had to hand carry these targets, and you lost half the targets because they were supported by a polymer film 50 angstroms thick. And so you had to hand carry them, but now you have to shoot them from a gun 20 times a second over 5 or 10 meters. So there are technical issues that are going to make that hard to commercialize. There are technical issues with neutron damage in magnetic confinement fusion we haven't solved. So not only haven't we solved them, we don't actually have a clue as to how to solve them, because in 1 year, all the atoms in the metal container move 100 times. And you have alpha decay, and the alpha decay makes helium and makes the stuff into Swiss cheese. And so those are fundamental problems that being a master in physics may not solve. Okay, so anyway, Omar Hurricane shares my skepticism as when fusion might become commercial, but not commercial, as opposed to a successful scientific experiment, but unlikely for 40 years. There's fission. These are examples of a large fission reactor or small modular reactors. A lot of people don't like fission for a number of reasons. In terms of safety, it's not that dangerous. These are the amount of deaths per unit of electricity per terawatt hour led by brown coal and coal. Anything where you burn something makes particulate matter, and these are the number of deaths. Whereas nuclear in here, it's a little bit safer than wind, a little bit more dangerous than solar, but it's really in the 4th decimal place. It's much more safe than hydropower, which dams break. But there's still inversion to nuclear. Don't worry, people are concerned about radiation. And so, but most people don't realize about a third of the non-CT scan type of stuff that you're exposed to is in the food you eat. So you are eating radioactivity. And for that reason, there's been a unit introduced called the BED, banana equivalent dose. I gave a talk in South Korea, and it turns out a cup of bok choy is the same as one banana. So it turns out you can use the same acronym, bok choy equivalent dose. These are other foods of servings of one banana equivalent, carrots, potatoes, red meat, lots of radioactivity in red meat, lima beans. So now, it's due to naturally occurring radiation, not due to thermonuclear testing. It's when neutron stars and supernova make radioactive stuff like potassium. The FDA knows full well that potassium is radioactive, and yet they say you should eat spinach and green beans and things like that, okay? Because the health benefits of having a nice diet outweigh the dangers of radiation. The people who are exposed to background radiation, it varies by a factor of 4 or 5, and there's no incidence of increases in cancer in that 4 or 5. Now, if you go a factor of hundreds more, then you begin to see something. But it's psychological. All right. Now, I talked about that. I'm a little bit off, so I'm going to go to here. I'm a little bit off here. Let me talk about agriculture. I know I'll try to swim through this very quickly. We had many industrial revolutions, energy revolution, telecommunications, computers, telephones, all that stuff. Agricultural revolution very quickly. The agricultural revolution, the third one was the invention of the Haber-Bosch process. You can make nitrogen fertilizers chemically, and it was awarded a Nobel Prize to Fritz Haber in 1918 for that. For the Haber-Bosch process, they realized they forgot about Bosch, so they gave him a Nobel Prize in 1931 for the Haber-Bosch process, and they made up a reason. They said it's for high temperature, high pressure catalysis, which was the original Haber-Bosch process. So they just try to fix the record, which was a good thing. So 2 Nobel Prizes. Another Nobel Prize went to Norman Borlaug, this one for peace, for developing dwarf strains of wheat that were much more productive, that could withstand large amounts of fertilizer and irrigation. Great stuff. the combination of fertilizer and crossbreeding of plants meant that from 1961 to 2021, where the population went from 3 billion to 7.9 billion, this is the land put under cereal production. It didn't change because productivity around the world increased so dramatically. But again, we have this problem, and the problem is that nitrogen in fertilizer emits N2O. The 3/4 to 80% of all the N2O is from agriculture. And so how do you prevent fertilizer not being used by the plant, which is most of it, from going to N2O? And so that's another thing. There are microbes that can feed plants that are being developed, but it's been proven, but it only works for half the fertilizer and doesn't work in all soils. So there's this so-called synthetic biology approach of making microbes that is a possibility. But again, we don't have the solution yet. And synthetic biology needs a boost. It takes too long to engineer the microbes. This took a better part of 8 years. And for different soils with different microbiome, you have to do faster than that. So that's another thing. Let me also say, I've got another 5 minutes, and so let me say that we are going to go over 450 parts per million. We're at 420 now. We're going to go over 550, probably go over 600 parts per million. And so we need to capture carbon dioxide, not only from electricity, but from we need to capture carbon dioxide that we can't capture. So let's say until we make jet fuel carbon-free, we need to do a lot of things. Until we solve the fertilizer problem, we need to do a lot of things. So, so let me remind you, we're emitting 52 billion tons of carbon equivalent a year, and an estimate was we would need 10 to 20 billion tons of air capture of CO2 in order to get anywhere close to keeping below 2.5 degrees. Forget about 2 degrees or 3 degrees. Okay, and so that's a lot of stuff. By comparison, 2 billion tons of solid landfill waste produced around the world every year. So we're talking 10 times the amount than landfill to be pumped underground. There are carbon capture methods available. This is one that was funded when I was Secretary of Energy. It was the first project that came on budget. What was the budget? It was $1 billion. It captured 1/4 of the coal plant carbon dioxide, 90% of 1/4. And it costs a lot of money. And these technologies cannot be used for air capture. So this is a real issue. I just want to mention the size of this plant. That's a big pickup truck, and it's big. And again, 1/4 of one coal plant. So it's been well known that if you make water very basic, pH 11, 12, you can capture a lot of the carbon dioxide goes into the water, becomes bicarbonate, and finally carbonate. And if you look at the solubility of carbon dioxide in water, by the time you're at pH 11 and 12, you can store the better fraction of a mole of carbon dioxide in water. That's a lot of carbon dioxide. A mole of gas, let me remind you, if it's a gas, standard temperature and pressure is 22 liters. And a mole in water is 1 liter. So that's a lot of carbon dioxide. If you turn it to an acid, you drop by, there's another order of magnitude here. So 1, 2, 3, 4, 5 orders of magnitude. So for that reason, people said, hey, if I can turn basic water into acidic water, then I can capture carbon dioxide using water, which is great. And but it turns out if you go from high pH, which is low proton concentration, to high pH, which is low pH, it's like electrons had the wrong sign. Anyway, low pH means high proton concentration. If you go from low to high, you're bucking entropy, because entropy wants to make things dilute. It wants to go from high concentration to low concentration. So there's a entropy second law that says how much energy you have to pay if you're going to change pH by changing protons. Okay? So you might think, wait a minute, I took freshman chemistry or high school chemistry. Isn't pH, and that's the energy penalty. And how could pH be changed without changing proton concentration? And so you got to look at the fine print. pH is defined as minus the log of the proton concentration times a fudge factor called the activity factor. What does activity factor mean? It means how useful are those protons, okay? And so let me just tell you, we found that a very, very common, widely used molecule, considered molecule for redox batteries is a molecule called TEMPO. This is what the molecule looks like. And when you take an electron off, it becomes charged. That nitrogen becomes charged. And in this molecular dynamics simulation of what's going on, these are water molecules. When it's oxidized, and the reds are oxygens, the whites are protons. And so the water molecules get a little line so the protons stick out and the water stick in. Whereas in reduced form, it's neutral, but it's different. Okay, so what we found is we take this molecule and take an electron off, the pH changes. So the gray is pH, and when the pH changes, due to the oxidation of the tempo, it gives up the carbon dioxide. So the idea is you put CO2 in the water, and then you just oxidize it, and then you let it release, and it comes back. Now, it not only captures carbon dioxide, but it's a wonderful, and so that doesn't mean anything to non-technical people. Let's just say that the energy being used to release the capture and release the carbon dioxide has now been decreased by a factor of 20. And we can know that this is working because if you take pH acid and just dump in base, it buffers and keeps the pH the same until you run out of the water molecules that are around the polarized charged molecule. And then it gives it up. The nice thing about this is, wait a minute, you have to take your electron off. So you need energy to take the electron off. But then on the round trip, it grabs the electron back, and our experiments show it compensates. Yes, you need energy to take it off, but you get it back. And so the only losses we are seeing so far are resistive losses. And we think we can lower the resistance by another factor of 10 by just engineering it better. So that's very exciting. I was tremendously excited. This might be my most important paper ever submitted to Science. And we got one review back and rejected it. So this has happened before, but never mind. I'm telling people the reaction to anything really new is you're wrong. Then they understand what's really happening. What's really happening is the water molecules are polarized. Hydrogen gets used up to turn bicarbonate into CO2. And this proton on the water molecule is polarized is much more likely to hop off the proton than normal water. And so it doesn't change the protons, but it maintains the protons that you started with. So it acts as a buffer. And our buffer experiment shows it's a buffer. So it does work, but never mind. You're wrong. Oh, that's obvious. The third reaction, you weren't the first to discover it. Anyway, will this be the best way of capturing CO2? Maybe, maybe not. It certainly will be one way that's it's certainly scalable and financially achievable. But plants are also pretty good. And I should point out that 10 to 20 billion tons of CO2 are converted into biomass every year. Most of that gets recycled back, 99.9%. And so growing forests is one solution. Let me propose another novel solution. It's a new material. It's called wood. And so you can make tall buildings. This is 20 stories tall, but most buildings are less than 4 or 5 stories. You got to do two things. If you make the structure out of wood and you don't tear down the building in 50 years, old London is made of wooden buildings that are 1,000 years, okay? So we know the technology it's called paint and keeping the wood dry. And so should there be a policy that says if you build a wooden building and don't tear it down for 100 years, 200 years, you should get credit for that. And so until we get carbon-free steel and concrete and other things, I advocate wooden buildings. One last little bit. I know I'm a few minutes over, but no, I'm okay. We're talking about sustainability, but I'm talking about population. And this is population growth, and we're a population of 8 billion people. And so in virtually every country in the developing world, or in all the world up until recently, we have more young people to support a smaller aging population. And so when the population begins to decline, the economists tell the leaders, you don't want this to happen. You want to encourage people to have more babies. This is called a Ponzi scheme. You want more new investors to pay off the old investors. And so, but people all over the world are choosing to have fewer children. Even India is fertility is approaching break even, and they're not rich in India. Okay? And China's one-child policy is now gone there, encouraging people not only have 2, but maybe 3. And the young people say, no, I don't want this. Not now. They're too expensive. They tend to hang around the house. You've got to pay for their IT. Okay, so anyway. Okay, so let me remind you of more history. In this transition from farming to mechanized farming, fewer farmers. Then displaced workers make stuff. They make washing machines and cars and stuff like that. But what do you do when you automate your factories? If you don't automate your factory, you're out of business. China's factories are more automated than U.S. factories because they're losing jobs to, Vietnam and Cambodia and Bangladesh. And so I think robots can actually do this, but there's going to be a time because robots are more expensive than minimum wage workers. I'm hoping in 10 or 20 years that won't be the case. And so when that happens, you can have rising prosperity without low-cost labor. And finally, I want to say that we need a new definition of wealth. The definition of wealth is GDP per capita. But GDP means you encourage you to build stuff, use stuff, throw away stuff. A higher GDP means you use a car for 10 years. Now cars last 25 or 30 years, but you don't want to, in order to increase the GDP, throw away the car. You build a building, tear down the building in 50 years, make a new building. China does this. So it increases the GDP, looks good, makes jobs, looks good. Okay, but that doesn't really, if you're in a developed country like the United States, it doesn't really talk to what's important. And so what do we care about in our lives? Well, we want our family and our neighborhoods to feel safe. We don't want our children to be killed in school. We don't want to be invaded by a hostile country. We want to be well-connected as we age and everything else like that. And so I'm going to close by quoting Robert Kennedy, not Jr., but Robert Kennedy Sr., who said this in 1968. And he said, the gross national product is not a lot for the health of our children, the quality of their education, or the joy of their play. It does not include the beauty of our poetry or the strength of our marriages, the intelligence of our public debate, or the integrity of our public officials. It measures neither our wit nor our courage, neither our wisdom nor our learning, neither our compassion or our devotion to our country. It measures everything, in short, except that which makes life worthwhile. He said that 1 month before he was assassinated. Thank you.
Thank you. We have time for a few questions.
Hey.
I have a question about nuclear power. That is, there's the concern about how much radiation you're having, but the concern is also about nuclear waste and nuclear proliferation.
Right.
So there's that question. And then there's also the question about the new nuclear reactors that are ultra small, and how good are they?
Okay, so first, very good question. It's not actually proliferation more than a terrorist going in there, stealing some nuclear material and making a dirty bomb. That's a real threat. The proliferation part comes from countries that create nuclear reactors and use the plutonium to make bombs. Okay, so nuclear, but in nuclear power in the United States, there's not that issue. And the nuclear reactors have to be guarded, and they have to have security, because you're always worried that some crazy might want to throw a plane at it or to do this. So there are armed guards, and it's a concern. The waste issue is also a concern. That has a technical solution. The other thing you can minimize the risk. And the technical solution, Sweden and Finland are doing things. There are technical solutions like improving drilling methods. So if you can drill something this big and go down a kilometer, you have access to much more geological sites. So there's a company that's trying to do that called Deep Isolation. This is Rich Muller and his daughter who started this company. But the same company are now trying to say, if you make a small modular reactor of this size, use 20% enriched uranium, which is legal, for non-proliferation, you can maybe run them for 20 years. So think of it as a battery, and then you're made in a factory, you use it, you put it back in the factory. So a lot of the accidental things, and they can be made so they will not melt down. Very, very low probability of melting down. Also the possibility you can put the whole thing after it's really done in a borehole. But other countries are figuring out how to do the spent fuel deposition. Also, using a few percent of the nuclear fuel, of the energy content of the fuel, instead of 1 or 2%, which is what we use today. Small modular reactors are being developed in a dozen countries. In order to be successful, you can't do it on 1 or 2 orders like NuScale, because they went 50% over budget, and the company that contracted them canceled the order. And so what you need is 100 orders to actually start marching down a learning curve. So whether nuclear takes off or not depends on all 3 things. The public safety concerns, the terrorism, the spent fuel, I think, are tolerable. The financial risk is a big unknown. Until you can build a nuclear reactor on budget, on time, small modular is a possibility because they can be mass-produced. You're not going to build many nuclear reactors. There are many countries doing that, but that remains a risk. Otherwise, there'll be natural gas. We do need some sort of compact energy source. Now, once you develop a really inexpensive but compact battery, you're in a different place. But the batteries, think cell phone to EV, think EV to utility scale. So EV, 70 kilowatt hours. Utility scale battery, hundreds of megawatt hours to gigawatt hours. And so a fire in a battery like that is bad news. So already the DOE said no more conventional electrolyte batteries, but they can catch fire. They have to be aqueous and things like that. But we don't have batteries will come along, whether they come along in 50 years. Or, oh, by the way, let me also say nuclear won't solve our problem in the next 30 years, because the time scale of getting a new generation is about 10 to 20 years. So, and don't hold your breath on fusion either. So anyway.
Let's do one more question, I think.
In the back? Yes, you.
So thank you so much for your talk. Early in your slides, you showed where we would go with our greenhouse gas emissions with no policies, and then what it's going to hopefully be with the current policies, and then if we put in more policies, potentially where we could go. And so you also spelled out, a number of solutions, a number of ways that we can address these problems. But I guess my question for you is, personally, do you find yourself optimistic, pessimistic, or like somewhere in the middle about like our ability as a world to meet these challenges?
In all honesty, I'm completely bipolar. That's why I need more lithium. Was we're not following current policies. And so my feeling is, I didn't talk about the battery research I'm doing. I did mention briefly CO2 capture. If you can make CO2 capture really, $50 a ton, if you can really make batteries $20 a kilowatt hour, it's a different world. At even $50 to $20 a kilowatt hour, you have no business. You can have a 400-mile car. Oh, by the way, another crucial thing about batteries is there's range anxiety. And most people, poor people, don't live in houses around the world. In the United States, we do live in houses. Or if they live in apartment complexes, they don't have charging stations. And so you want to go back to a service station model where you can charge your battery. So suppose you, out of 400 miles or 350 miles, you can go 200 miles in 5 minutes. Just pretend. No problem. You don't have to put expensive charging stuff in your home. You don't have to use just go and charge your car. And since the battery lasts longer than the bladder when you're on a long trip, while you're discharging, your car is charging. And the gasoline stations like it, because if you have to spend 5 minutes buying stuff, they love it. They don't want you to spend 10 minutes because you're blocking other customers. It's true. And gasoline stations, I learned this because I was advising Royal Dutch Shell for a while, and they make more money selling junk in gasoline stations than diesel and gasoline. Soda, beer, magazines, cigarettes, stuff like that. So 5 minute charging time means you go back to service station model, and you only have range anxiety when you have long trips. And so that's a technology thing. And so do I think fast charging will become a reality? And the answer is yes. And I'm working on that, but we actually, the standard now is C/3. That's 3 charges in 3 hours for a charge-discharge cycle. Now they're asking for 1C and going to 3C. So 20 minutes for the full range means 5 minutes, you get 150, 200 miles. Okay, so I'm a big believer in these technological innovations. When they occur, transition is rapid. One of the most rapid transitions was going from horses in cities to cars because of the horse poop problem. Manhattan was filling up with horse poop, ankle deep in horse poop. And so this is a pollution you can see and smell and everything. And then along comes a poopless carriage, and it was like gold. And so in 20 years, cities just made this transition. You will see a similar thing once cars cost $20,000, $25,000 and can go 350 miles, and you can charge fast because there's no maintenance, very little maintenance in an electric vehicle. And so as a technologist, I'm hoping that these technologies happen and that transition really happens fast. If you need to use policy to push people, it always goes slower. And that's the issue. So when I was saying I've always pushed research and innovation, I was against spending billions on charging stations. I said I want to make a better battery. I still feel that way. I want to make a better battery.
Great. Let's continue the conversation in the atrium at the reception, and thanks, Dr. Chu, again for a wonderful presentation.